For years, science fiction writers from Edgar Rice Burroughs to C.S. Lewis have imagined what it would be like for humans to walk on Mars. As mankind comes closer to taking its first steps on the red planet, authors' depictions of the experience have become more realistic. Andy Weir's The Martian begins with a massive dust storm that strands fictional astronaut Mark Watney on Mars. In the scene, powerful wind rips an antenna out of a piece of equipment and destroys parts of the astronaut's camp. Mars is infamous for intense dust storms, which sometimes kick up enough dust to be seen by telescopes on Earth. Every year, there are some moderately big dust storms that pop up on Mars, and they cover continent-sized areas and last for weeks at a time, said Michael Smith, a planetary scientist at NASA's Goddard Space Flight Center in Greenbelt, Maryland. Beyond Mars' large annual storms are massive storms that occur more rarely but are much larger and more intense. Once every 3 Mars years, about 5.5 Earth years, on average, normal storms grow into planet-encircling dust storms, and we usually call those global dust storms to distinguish them, Smith said. It's unlikely that even these dust storms could strand an astronaut on Mars, however. Even the wind in the largest dust storms likely could not tip or rip apart major mechanical equipment. The winds in the strongest Martian storms topped out at about 60 miles per hour, less than half the speed of some hurricane-force winds on Earth. Focusing on wind speed may be a little misleading as well. The atmosphere on Mars is about 1% as dense as Earth's atmosphere. That means to fly a kite on Mars, the wind would need to blow much faster than on Earth to get the kite in the air. The key difference between Earth and Mars is that Mars' atmospheric pressure is a lot less, said William Farrell, a plasma physicist who studies atmospheric breakdown in Mars dust storms at Goddard. So things get blown, but it's not with the same intensity. The difficulties of solar power. A dust storm on Mars in 2008 temporarily cuts the amount of sunlight reaching the solar array on NASA's Mars exploration rover Spirit, leaving the rover in a vulnerable state. Mars dust storms aren't totally innocuous, however. Individual dust particles on Mars are very small and slightly electrostatic, so they stick to the surfaces they contact like styrofoam packing peanuts. If you've seen pictures of Curiosity after driving, it's just filthy, Smith said. The dust coats everything, and it's gritty. It gets into mechanical things that move, like gears. The possibility of dust settling on and in machinery is a challenge for engineers designing equipment for Mars. The dust is an especially big problem for solar panels. Even dust devils of only a few feet across, which are much smaller than traditional storms, can move enough dust to cover the equipment and decrease the amount of sunlight hitting the panels. Less sunlight means less energy created. In The Martian, Watney spends part of every day sweeping dust off his solar panels to ensure maximum efficiency, which could represent a real challenge faced by future astronauts on Mars. Global storms can also present a secondary issue, throwing enough dust into the atmosphere to reduce sunlight reaching the surface of Mars. When faced with a larger dust storm in the book, Watney's first hint is the decreased efficiency of his solar panels caused by a slight darkening of the atmosphere. That's a pretty accurate depiction of what large dust storms can do, Smith said. When global storms hit, surface equipment often has to wait until the dust settles, either to conserve battery or to protect more delicate hardware. We really worry about power with the rovers. It's a big deal, Smith said. The Spirit and Opportunity rovers landed in 2004, so they've only had one global dust storm to go through in 2007, and they basically shut down operations and went into survival mode for a few weeks. Stirring up dust devils. Large global dust storms put enough dust in the air to completely cover the planet and block out the sun. But doing so ultimately dooms the storm itself. The radiative heat of sunlight reaching the surface of the planet is what drives these dust storms. As sunlight hits the ground, it warms the air closest to the surface, leaving the upper air cooler, as in thunderstorms on Earth. The warm and cool air together become unstable, with warm air rising up and taking dust with it. A towering dust devil casts a serpentine shadow over the Martian surface in this image acquired by the high-resolution image science experiment HiRISE camera on NASA's Mars Reconnaissance Orbiter. The scene is a late spring afternoon in the Amazonias Planitia region of northern Mars. The view covers an area about 0.4 of a mile, 644 meters across. North is towards the top. The length of the dusty whirlwind shadow indicates that the dust plume reaches more than half a mile, 800 meters in height. The plume is about 30 yards or meters in diameter. Rising plumes of warm air create everything from small dust devils similar to those that form in deserts on Earth to larger continent-sized storms. These larger storms sometimes combine into the global storms, which cover the entire planet in atmospheric dust. Larger storms typically only happen during the summer in Mars' southern hemisphere. Seasons on Mars are caused by the tilt of the planet, like on Earth, but Mars' orbit is less circular than Earth's. For part of a Martian year, the planet is closer to the Sun and therefore significantly hotter. This warmer time is during the southern hemisphere summer, so radiative heat forces are strongest then. Once started, bigger storms can last weeks to months. Scientists aren't really sure why the years-long gaps between the storms exist. It could be that it just takes a while for the sources to replenish themselves, Smith said. Maybe there's some kind of cycle that the dust has to go through to get back into the right places to trigger a new one, or maybe it's just kind of luck. Scientists have been tracking these global dust storms on Mars for more than a century, using both telescopes on Earth and spacecraft orbiting Mars. The storms have been observed a number of times since 1909, most recently in 2007. Now, more than 8 years later, Smith is hopeful he'll get the chance to study a major storm soon. Rough terrain and nasty weather. The Curiosity rover's wheels have taken a beating thus far on Mars, and the road ahead may be even rockier. The 1-ton robot has just crossed out of its landing ellipse, the 12 by 4 mile, 19 by 7 kilometer zone that was targeted for its dramatic August 2012 touchdown, and is now moving toward an increasingly challenging landscape called the Zabriskie Plateau, mission team members said. We're heading out into very rough terrain, Curiosity project scientist John Grotzinger, a geologist at the California Institute of Technology in Pasadena, said during a presentation at the 8th International Conference on Mars, which took place at Caltech last week. These rocks have been a problem for us. Curiosity last July embarked on a roughly 5-mile, 8-kilometer drive to the base of Mount Sharp, which has long been its ultimate science destination. The car-sized rover has about 2 miles left to go, researchers said. Toward the end of 2013, Curiosity encountered a region studded with sharp rocks, which presented the mission with a major technical challenge. Unlike what has been experienced by other Mars rovers, these rocks were embedded in the surface like spikes in a parking lot exit. In previous encounters with such obstacles, most rolled over and did not present a risk to the rover wheels. The sharp rocks, looking like 3 and 4-inch, 7.6 and 10.2 centimeters shark's teeth, appeared to be wind-sculpted. Soft formations, apparently overly harder rock, and as the wind scours the region, what's left behind are the jagged remains of the tough subsurface stuff. The wind becomes a big problem for our wheels, Grotzinger said. As the rocks fall apart, they're sculpted by the wind to points that we see as we drive along. Grotzinger and Curiosity rover planner team, led by Chris Roumeliotis, displayed to the audience at Caltech graphic images of wheel wear captured by Curiosity's cameras. We did an inventory of the wheels, Grotzinger said, and here's the image that set us into a constructed panic. The mosaic showed wheels that had been dented, punctured, and even torn by the rocks below. To figure out what to do, you take a picture of a metal wheel, he added, and when you see the planet on the other side, i.e. through a large hole in the wheel, unless it says JPL, it's a problem. The JPL phrase refers to the holes that had been engineered into the wheels to mark the rover's path in the sandy surface. These holes spell out JPL in Morse code, but the Martian landscape could be clearly seen through additional rips and tears in the metal. An extensive testing campaign was immediately initiated both at JPL's Mars Yard, a rocky surface setup at the lab, as well as in the field near California's Death Valley. Roumeliotis showed a video of one such test It used a roughly 3-inch by 1-inch, 7.6 by 2.5 centimeter aluminum spike with a dull point to simulate a sharp rock. "Welcome to the Impaler," Roumeliotis said as the rover drove over the spike and its wheel's surface tore like wet paper. There was a visceral gasp from the audience. Roumeliotis pointed out that such damage only occurred when the rover was driving forward, due to the pivot points of the suspension system. A similar video of the rover driving backwards showed the wheels traversing the spike with no ill effects. In the months ahead, the rover will therefore be driving backward across some of the worst areas, as it did when crossing the last rocky patch. This results in less damage, and what does occur tends to affect 2 wheels and not 4 when driving in this mode, team members said. In a later conversation, Grotzinger pointed out that the real strength in Curiosity's beer keg-sized wheels lies not in the tread surface, but rather in the metal ridge and flexible spokes inside. The internal rim and the flexible spokes really absorb much of the punishment, he said. The rover team considered 7 different pathways for the remaining distance between Curiosity's current location and the 3.4-mile-high, 5.5-kilometer Mount Sharp, whose many rock layers record a history of Mars' changing environmental conditions over time. Curiosity will descend into a shallow, sandy-floored valley to avoid the worst of the upcoming terrain. The rover team plans to skirt the deeper sand by hugging the edge of the valley floor, where the drift thins out near the wall. Someone posted Robert Frost's poem, "The Road Less Taken," at JPL in tribute to the challenging choices ahead. Grotzinger told the crowd, the choice seemed fitting. Mars radiation and the lack of gravity. On August 7, 1972, in the heart of the Apollo era, an enormous solar flare exploded from the sun's atmosphere. Along with a gigantic burst of light in nearly all wavelengths, this event accelerated a wave of energetic particles, mostly protons, with a few electrons and heavier elements mixed in. This wash of quick-moving particles would have been dangerous to anyone outside Earth's protective magnetic bubble. Luckily, the Apollo 16 crew had returned to Earth just 5 months earlier, narrowly escaping this powerful event. In the early days of human spaceflight, scientists were only just beginning to understand how events on the sun could affect space, and in turn how that radiation could affect humans and technology. Today, as a result of extensive space radiation research, we have a much better understanding of our space environment, its effects, and the best ways to protect astronauts, all crucial parts of NASA's mission to send humans to Mars. The Martian film highlights the radiation dangers that could occur on a round trip to Mars. While the mission in the film is fictional, NASA has already started working on the technology to enable an actual trip to Mars in the 2030s. In the film, the astronauts' habitat on Mars shields them from radiation, and indeed, radiation shielding will be a crucial technology for the voyage. From better shielding to advanced biomedical countermeasures, NASA currently studies how to protect astronauts and electronics from radiation, efforts that will have to be incorporated into every aspect of Mars mission planning, from spacecraft and habitat design to spacewalk protocols. The space radiation environment will be a critical consideration for everything in the astronauts' daily lives, both on the journeys between Earth and Mars and on the surface, said Ruth Ann Lewis, an architect and engineer with the Human Spaceflight Program at NASA's Goddard Space Flight Center in Greenbelt, Maryland. You're constantly being bombarded by some amount of radiation. Radiation at its most basic is simply waves or subatomic particles that transport energy to another entity, whether it's an astronaut or spacecraft component. The main concern in space is particle radiation. Energetic particles can be dangerous to humans because they pass right through the skin, depositing energy and damaging cells or DNA along the way. This damage can mean an increased risk for cancer later in life, or at worst acute radiation sickness during the mission if the dose of energetic particles is large enough. Fortunately for us, Earth's natural protections block all but the most energetic of these particles from reaching the surface. a huge magnetic bubble called the magnetosphere, which deflects the vast majority of these particles, protects our planet, and our atmosphere subsequently absorbs the majority of particles that do make it through this bubble. Importantly, since the International Space Station, ISS, is in low Earth orbit within the magnetosphere, it also provides a large measure of protection for our astronauts. We have instruments that measure the radiation environment inside the ISS where the crew are, and even outside the station, said Carrie Lee, a scientist at NASA's Johnson Space Center in Houston. This ISS crew monitoring also includes tracking of the short-term and lifetime radiation doses for each astronaut to assess the risk for radiation-related diseases. Although NASA has conservative radiation limits greater than allowed radiation workers on Earth, the astronauts are able to stay well under NASA's limit while living and working on the ISS within Earth's magnetosphere. But a journey to Mars requires astronauts to move out much further beyond the protection of Earth's magnetic bubble. There's a lot of good science to be done on Mars, but a trip to interplanetary space carries more radiation risk than working in low Earth orbit, said Jonathan Pellish, a space radiation engineer at Goddard. In this image, taken by the Viking 1 orbiter in June 1976, the translucent layer above Mars' dusty red surface is its atmosphere. Compared to Earth's atmosphere, the thin Martian atmosphere is a less powerful shield against quick-moving, energetic particles that pelt in from all directions, which means astronauts on Mars will need protection from this harsh radiation environment. A human mission to Mars means sending astronauts into interplanetary space for a minimum of a year, even with a very short stay on the red planet. Nearly all of that time they will be outside the magnetosphere, exposed to the harsh radiation environment of space. Mars has no global magnetic field to deflect energetic particles, and its atmosphere is much thinner than Earth's, so they'll get only minimal protection even on the surface of Mars. Throughout the entire trip, astronauts must be protected from two sources of radiation. The first comes from the sun, which regularly releases a steady stream of solar particles, as well as occasional larger bursts in the wake of giant explosions, such as solar flares or coronal mass ejections on the sun. These energetic particles are almost all protons, and though the sun releases an unfathomably large number of them, the proton energy is low enough that they can almost all be physically shielded by the structure of the spacecraft. Since solar activity strongly contributes to the deep space radiation environment, a better understanding of the sun's modulation of this radiation environment will allow mission planners to make better decisions for a future Mars mission. NASA currently operates a fleet of spacecraft studying the sun and the space environment throughout the solar system. Observations from this area of research, known as heliophysics, help us better understand the origin of solar eruptions and what effects these events have on the overall space radiation environment. If we know precisely what's going on, we don't have to be as conservative with our estimates, which gives us more flexibility when planning the mission, said Pellish. The second source of energetic particles is harder to shield. These particles come from galactic cosmic rays, often known as GCRs. They're particles accelerated to near the speed of light that shoot into our solar system from other stars in the Milky Way or even other galaxies. Like solar particles, galactic cosmic rays are mostly protons. However, some of them are heavier elements ranging from helium up to the heaviest elements. These more energetic particles can knock apart atoms in the material they strike, such as in the astronaut, the metal walls of a spacecraft, habitat, or vehicle, causing subatomic particles to shower into the structure. The secondary radiation, as it's known, can reach a dangerous level. There are two ways to shield from these higher energy particles and their secondary radiation. Use a lot more mass of traditional spacecraft materials, or use more efficient shielding materials. The sheer volume of material surrounding a structure would absorb the energetic particles and their associated secondary particle radiation before they could reach the astronauts. However, using sheer bulk to protect astronauts would be prohibitively expensive, since more mass means more fuel required to launch. Using materials that shield more efficiently would cut down on weight and cost, But finding the right material takes research and ingenuity. NASA is currently investigating a handful of possibilities that could be used in anything from the spacecraft to the Martian habitat to spacesuits. The best way to stop particle radiation is by running that energetic particle into something that's a similar size, said Pellish. Otherwise, it can be like you're bouncing a tricycle off a tractor trailer. Because protons and neutrons are similar in size, one element blocks both extremely well: hydrogen, which most commonly exists as just a single proton and an electron. Conveniently, hydrogen is the most abundant element in the universe and makes up substantial parts of some common compounds, such as water and plastics like polyethylene. Engineers could take advantage of already required mass by processing the astronauts' trash into plastic-filled tiles used to bolster radiation protection. Water, already required for the crew, could be stored strategically to create a kind of radiation storm shelter in the spacecraft or habitat. However, this strategy comes with some challenges. The crew would need to use the water and then replace it with recycled water from the advanced life support systems. Polyethylene, the same plastic commonly found in water bottles and grocery bags, also has potential as a candidate for radiation shielding. It's very high in hydrogen and fairly cheap to produce. However, it's not strong enough to build a large structure, especially a spacecraft, which goes through high heat and strong forces during launch. And adding polyethylene to a metal structure would add quite a bit of mass, meaning that more fuel would be required for launch. We've made progress on reducing and shielding against these energetic particles, but we're still working on finding a material that's a good shield and can act as the primary structure of the spacecraft, said Sheila Thibault, a materials researcher at NASA's Langley Research Center in Hampton, Virginia. One material in development at NASA has the potential to do both jobs: hydrogenated boron nitride nanotubes, known as hydrogenated BNNTs, are tiny nanotubes made of carbon, boron, and nitrogen, with hydrogen interspersed throughout the empty spaces left in between the tubes. Boron is also an excellent absorber of secondary neutrons, making hydrogenated BNNTs an ideal shielding material. This computer simulation, based on data from NASA's Mars Atmosphere and Volatile Evolution, or MAVEN spacecraft, shows the interaction of the streaming solar wind with Mars' upper atmosphere. MAVEN is gathering information on the space environment at Mars, information that will be key to planning a human mission to Mars in the 2030s. This material is really strong, even at high heat, meaning that it's great for structure, said Thibault. Remarkably, researchers have successfully made yarn out of BNNTs, so it's flexible enough to be woven into the fabric of spacesuits, providing astronauts with significant radiation protection even while they're performing spacewalks in transit or out in the harsh Martian surface. Though hydrogenated BNNTs are still in development and testing, they have the potential to be one of our key structural and shielding materials in spacecraft, habitats, vehicles, and spacesuits that will be used on Mars. Physical shields aren't the only option for stopping particle radiation from reaching astronauts. Scientists are also exploring the possibility of building force fields. Force fields aren't just the realm of science fiction. Just like the Earth's magnetic field protects us from energetic particles, a relatively small, localized electric or magnetic field would, if strong enough and in the right configuration, create a protective bubble around a spacecraft or habitat. Currently, these fields would take a prohibitive amount of power and structural material to create on a large scale, so more work is needed for them to be feasible. The risk of health effects can also be reduced in operational ways, such as having a special area of the spacecraft or Mars habitat that could be a radiation storm shelter, preparing spacewalk and research protocols to minimize time outside the more heavily shielded spacecraft or habitat, and ensuring that astronauts can quickly return indoors in the event of a radiation storm. Radiation risk mitigation can also be approached from the human body level. Though far off, a medication that would counteract some or all of the health effects of radiation exposure would make it much easier to plan for a safe journey to Mars and back. Ultimately, the solution to radiation will have to be a combination of things, said Pellish. Some of the solutions are technology we already have, like hydrogen-rich materials, but some of it will necessarily be cutting-edge concepts that we haven't even thought of yet. The planet Mars has few things in common. Both planets have roughly the same amount of land surface area, sustained polar caps, and both have a similar tilt in their rotational axis, affording each of them strong seasonal variability. Additionally, both planets present strong evidence of having undergone climate change in the past. In Mars' case, this evidence points toward it once having a viable atmosphere and liquid water on its surface. At the same time, our two planets are really quite different, and in a number of important ways. One of these is the fact that gravity on Mars is just a fraction of what it is here on Earth. Understanding the effect this will likely have on human beings is of extreme importance when it comes time to send crewed missions to Mars, not to mention potential colonists.